Hey, what's up, guys? Welcome back to Two Men One Course podcast. Another day, another episode. Well, but we're happy to see you. Okay. Tyler will show up in a little bit, but before that, we'll have something to talk about. All right. Same drill. I got a joke of the day. One question for you. Anyone here knows what kind of bird is always getting hurt? What kind of bird is always getting hurt? Ow, ow, ow. All right. All right, lab 10. This is the last lab of this semester. Are you guys ready? All right, let's talk about what you're gonna do in the lab. So we have you will extract the DNA from fruit samples and then characterize its purity and its concentration. Okay. Now, I decided not to talk about the structure of DNA. I think you guys learned about that and save that. So I'm gonna teach Tyler. Last time he learned this, he was a baby, probably. Anyway, so all right, for us, that's what you need to know for the lab. Okay. Now, you're gonna extract DNA. There are three things that you have to do to extract DNA. First off, where is the DNA? I think you guys know. It's in the nucleus of the cell. Okay. So to get the DNA out, you have to break the cell first. So break the cell membrane. That's the first task. Okay, remove a solid residue, the protein. I think everything that you know inside the cell. Okay, and precipitate the DNA so we can get it as a solid. All right. Now start with the first task: breaking the cell. Right, breaking the cell membrane. To do that, now let's talk about the structure of the cell membrane. Anyone here know what a cell membrane is made out of? We call it a phospholipid bilayer. Okay, and I think you've learned that in a biology class or cell class, right? So you're gonna and a molecule of the phospholipid contain the phosphate group, which is a highly polar at the top. We call polar head or hydrophilic head and hydrophobic tail. Okay, non-polar tail. All right. It's hard to interact with this because it's got the polar group and non-polar and a dissolved light that's hard to apply in here. Yeah, because you got the two way like opposite polarity. But that's one compound that can interact with the phospholipid bilayer, and that is a soap or detergent. That's a soap that we usually use in the laboratory, Alconox, I think is how they say it. All right. The detergent of the soap, no, the molecule of the detergent of the soap look just like this. It's a fatty acid chain, right? So we got polar head and non-polar tail. Just very similar to the phospholipid, right? I think some of you know the how soap work, like to clean up fat or oil residue from the plate, from dishes, or from your body. So from myself, the soap molecule would use the non-polar tail, interact with the dirt or something, the non-polar, the fat interact like that. A bunch of it, right? From myself. All right, so myself, just a bunch of it. The polar head outside, it point out, so it means that this guy is soluble in water, can interact with water, and we can wash off using just water. Same thing, same drill. Each molecule of the soap or detergent molecule can interrupt the phospholipid, right, and form the micelle for each part of the cell membrane. So interrupt the cell membrane and break it, basically. So the first task, breaking cell membrane, we're gonna use the detergent. Okay, so you're gonna shake it, destroy the cell membrane. The second step, remove solid residue. All right, after you use the detergent, cell membrane has already been broken. Okay, and you're gonna filter anything solid. The DNA still stay in the solution. You don't have to worry about it. It will just go through. All right, the filtrate that contains your DNA. And the last step is we want to keep the DNA as a solid form. Right now, DNA is in solution. We have to precipitate it. All right. Anyone here knows if DNA is soluble in water or not? DNA actually soluble in water, right? The reason that DNA is soluble in water because the phosphate group and the polar group in DNA interact with water, usually hydrogen bonding. Okay, really strong interaction, and that's why DNA is soluble in water. Now, what's going to happen if we remove some of the interaction with water? When that happens, of course, the solubility in water of DNA would drop, would decrease. Okay, so we can do that by adding a sodium ion. We usually use sodium acetate. All right, the sodium ion will pair up with the phosphate group, form a strong ionic bond. So basically, there'll be less water that can interact with the DNA, and this DNA become less water soluble. Okay, so we're going to precipitate DNA in ethanol. Ethanol is less polar than water, so just facilitate that precipitation process and add sodium acetate to lower the solubility of the DNA even less. Okay, eventually you're gonna get the DNA look something like that in the solution. Pretty cool. Get your phone ready, guys. Be real with. Take a picture. All right. So and at the very end, you analyze the concentration and the purity of the DNA. And of course, this DNA that you're gonna get is an extracted DNA. It's not gonna be pure. It will contain protein, some mixture. Okay, so you're gonna use a spectrophotometer, and it can read the absorption of the DNA and a protein, and we determine the purity of this protein. Now, before that, let's imagine in your DNA solution, contain DNA and contain protein. Okay, most of the protein anyway. All right, we'll use spectrophotometer, which means that these two components, the protein and the DNA, have to be able to absorb light, let's UV or visible light. Okay, the question is, can proteins absorb light? I'm not sure you learn in Gen Chem lecture, but actually it can, right? Those who have aromatic group like tryptophan, tyrosine, histidine, this guy can absorb the UV at 280 nanometer. Okay, remember this wavelength, wavelength real quick. So protein absorb light, have the maximum wavelength, like the highest absorption at 280. Okay, that's the maximum absorption. DNA though can also absorb light from nucleobases. It got aromatic group. You know that? But the lambda max, the highest maximum absorption, is not at 280. It's at 260 nanometer. If you have a mixture between the DNA and the protein, you're gonna see the two absorption at 260 and 280. But the ratio will tell you the purity of it. Okay, we're gonna use absorption as to represent the concentration. Of course, imagine if you have a lot of DNA, the absorption is high. If you have a low DNA, absorption is low, according to Beer's law. Okay, so we're gonna take the ratio of absorption at 260, which is represent the concentration of DNA, and the absorption at 280, which represent the concentration of proteins. And if this ratio is 1.8 or higher, that's a pure DNA. Yeah. Hopefully you get to this number at 1.8 or higher. All right, and now, so that's how we assess the purity of the DNA solution. The concentration, here's how we do it. Only if you have the pure DNA. Okay, and again, pure means 1.8 or higher. That's pure. All right, if you have a pure DNA sample, a concentration of absorption of 1 of a pure DNA, that is 50 ppm, microgram per milliliter. All right. So if you have a 1.8, you have to do the math in a little bit. So because 1 of pure DNA samples is 50 microgram per milliliter, 1.8, how much is that? Do the math on that. All right. All right. Let's practice together real quick. All right. So a DNA extract sample exhibit the UV visible spectrum below. There we go. Is this DNA sample pure? How do you determine it? Well, this two absorption, the 260 nanometer, that's from DNA, and the 280 from protein. Okay, if the ratio of 260 over 280 nanometer is 1.8 or higher, that's a pure DNA sample. So we take absorbent of 260 over absorbent of 280, 0.9124 over 0.4612, and then 0.9. That's a pure DNA. Now, very sample calculation, see that? All right. Now, the next one, you have to calculate the concentration of this DNA sample in microgram per milliliter. If you remember that the concentration of absorbent of 1 of a pure DNA sample is 50 microgram per milliliter. All right. So this is what we're going to do. The unit that we want is microgram per milliliter. What we have, I'll take a look. So we're going to have 50 microgram per milliliter. That's 1 absorbent. Yeah, absorption of 1. Right now we have 0.9124 absorption. Absorbent cancel out. You get the concentration of 45.62 microgram per milliliter, or 26646. That's it. All right, very simple. All right, why are we interested in DNA? In this lab, there are a bunch of application of DNA. I think you guys learn from the textbook application, textbook what DNA do, why is it important. Now let's go outside. You might have heard the forensic science, DNA fingerprint and profiling. All right, so we can take like white blood cell, semen, skin, lip print, or saliva, and that's contain our DNA in it, and we use that in crime scene, yeah, to find a suspect. Okay, and we just develop the like things that you find from crime scene against the suspect A and suspect B of DNA, and you see and compare and contrast. All right. Now I'm gonna take you to a tour. Okay. Now this is the first DNA profiling in forensic science. I'm gonna take you to Leicester in England, right there. What happened is we're going to go back in time, 1983. A 15-year-old girl named Linda Mann was abducted in Leicestershire, England, which Leicestershire is a neighborhood in Leicester, England. Okay. The next day, well, of course, the police came out, the parents worried, right? The next day, her body was discovered raped and murdered, and they couldn't find the murderer. 3 years later, sadly, another young woman met the same fate in Enderby, England, which is like right next to Leicestershire. Yeah, same thing, got raped, murdered, and we found her body in the wood. Right? Well, couldn't find anyone. Right? In the same year, there's one suspect. His name is Richard Buckland. Buckland was arrested, and he confessed to the second murder only, not the first one. Okay, and Buckland was about to subject to life sentence in prison. And at the same time, well, before you arrest someone, you have to prove that this guy is actually like the murderer. So the University of Leicester took his DNA sample, compared the DNA sample from semen from the crime scene, and test against Buckland's DNA. It didn't match. Okay, Buckland became the first person to be proven innocent by DNA fingerprint. Well, not like being happy about, hey, you're the first person, but not in this way. But that's the very first time that we use DNA profiling in forensic science. Okay, and ultimately Buckland was proven innocent. Buckland said that he what's the word for it? Got pressured by the police, and he just like give up and say, oh, I committed the crime, but actually he did not. Right. Now the year later, so they want to take this crime further because this keep happening. All right, so in 1987, a year later, 5,500 men in the local area in Leicester, England, were tested. Okay, now we have one guy, his name is Colin Pitchfork, persuaded his colleague Ian Kelly to test in his place. All right, Pitchfork worked in a bakery in town, and this guy had a prior conviction for multiple sexual harassment, and he actually exposed himself to more than 1,000 women beginning at his early teen. Probably have a really serious problem. He asked his co-worker Ian Kelly to do blood test in place of him, and the reason is to avoid being harassed by police due to his past. Well, obviously. This plan was overheard and reported by a local Pitchfork genetic profile matched the semen sample, and not only one but both cases in 1983 and 1986. Right? Pitchfork was finally arrested in 1987, 4 years after the first murder was committed. It took years until this happened. It was sad, but that's science takes some time. Okay, and crime takes some time. But that's the first example of using the DNA fingerprint in forensic science and in the crime. All right. So before that, next video, Tyler gonna come in. We're gonna talk about like what you need to do in the lab. Let's go.